In the next few lectures, we're going to carry on with our program, which is translating some very well-known results of classical analysis to our context of differentiable maps between differentiable manifolds. More precisely, today, we are going to treat the inverse function theorem and the local normal form of immersions. An upside of working with differentiable maps is that the local behavior on f of f and its derivative is similar at points that we are going to call right now regular for lack of a better name. But later on, we're going to make more precise what we mean. For instance, let's begin this lecture with the definition of immersion, which is a concept that it is studied in analysis courses. Let's consider a differentiable map between differentiable manifolds. We say that this map is an immersion at a certain point x if the differential of f at that point, which is a linear map between linear vector spaces, is injective. We have to realize that this tangent space, the tangent space to M at a point has dimension M, and that the tangent space of N at one of its points has dimension N. And that in order to have an injective mapping, we need to have the condition M less or equal than N. Otherwise, this linear map is never going to be injective. We say that F is an immersion if F is an immersion at every of its points. So this is a definition that we know from the courses of analysis, in which we are just considering the Jacobian matrix and requiring it to have maximal rank, and also to satisfy that the number of columns is less or equal than the number of lines. Okay, here we have the analog for the differentiable case, for the case of abstract manifolds. Let us consider an immersion between spaces of the same dimension. In such a case, the differential of f at the point x, if we are working with an immersion at x, is an injective linear map from the tangent space of M at x to the tangent space of N at f of x. Okay? But if M and N have the same dimension, then these two vector spaces have also the same dimension. And this linear map is injective if and only if it is an isomorphism, a linear isomorphism. So that's the situation we're going to be in. And this is the context in which we can apply the inverse function theorem, which is as follows. Let F be a differentiable map between manifolds of the same dimension, which is an immersion. Then F is local diffeomorphism. And this is a local theorem. And as such, the idea, as it's going to happen with many local theorems, is that we can actually introduce this result into the setting or the situation. We can transfer it to the setting of differentiable maps between Euclidean spaces, and then applying the result that we already know from the courses of analysis. So let's see that this perspective, this point of view, works very well in this case. Right? We have a map between the map F, a differentiable map between manifolds. Here We have the point x, and here the point f of x. This is the manifold M, and this is the manifold N. Here it's not clear so far that we can apply the inverse function theorem, but we can consider the expression of f in local charts. And that's going to be a situation in which we're going to be able of applying the usual inverse function theorem. Let's see how. We consider a local chart for the first manifold defined in a neighborhood of the point x. Let's call this local chart, for instance, phi. The image of phi is going to be some open subset of R to the n, where n is the dimension of our two manifolds. Okay, it is an open subset of R to the n containing the point phi of x. In the same way, we can consider now a local chart for the second manifold. Let's call it psi. And in that way, we are going to get to R to the n. The n is the same for the two manifolds because these two manifolds have the same dimension. So here we have the point psi of f of x. And there is a map that is actually closing the diagram, which is the expression of f in these two local charts, phi and psi. All right? This is the composition of the inverse of phi, f, and psi. So what happens now? We know by hypothesis that f is an immersion at the point x. This is our hypothesis. But let's remember for a minute that phi can be interpreted as a diffeomorphism between an open subset of the manifold M and an open subset of R to the n with the usual differentiable structure. And in the same way, psi can also be interpreted as a diffeomorphism. Since these two maps over here are diffeomorphisms, f is an immersion at the point x if and only if the expression of f in local charts is an immersion at the point phi of x. So let's write that property down. Okay, but now we can apply the inverse function theorem to this map because this map is now a map between the Euclidean spaces. So we are allowed to apply the inverse function theorem. So this is going to be a local diffeomorphism. Okay, in a neighborhood of x, if you want. And again, since phi and psi are diffeomorphisms, then f is also going to be a local diffeomorphism. So this property is indeed the property that we know for differentiable maps between Euclidean spaces. It's nothing else, because the way in which we prove it is just considering the expression of f in local charts and then applying the result that we already know. Okay? The downside of the inverse function theorem is that in this case, in which we have an immersion between manifolds of the same dimension, f is a local diffeomorphism, but it is not a diffeomorphism. That's the problem. And we can actually give an example. Consider the map f defined over here from the line to the circle. given by the image of x is cosine of x, sine of x. The map F is local diffeomorphism, but it is not a diffeomorphism. What happens is that the differential of F can be interpreted as a map from the tangent space to R at X that can be identified with a real line to the tangent space of R2 at the point f of X. It can be interpreted as a map from R to R2. And the matrix, indeed, is going to be a 2-by-1 matrix. The entries of such a matrix are the derivatives of the components of F. So the derivative of the cosine is minus sine, right? And the derivative of the sine, sorry, it's the cosine. Since this matrix is never vanishing because either sine or cosine are different than 0, then the differential of f at x is injective. But this differential is going to be also a map from the tangent space of R at X, which again can be identified with the line, to the tangent space of circle at the point of X. So, and of course it's going to be injective because it is essentially the same map. So, and these two spaces over here right now are of dimension 1 because they are tangent spaces of manifolds of dimension 1. So we are in the situation of the inverse function theorem, and because of that, F is a local diffeomorphism, as it is very well known. But it is not a diffeomorphism because it is not injective, for instance. If we consider f of x, this is equal to f of x plus 2 pi, because the trigonometric functions are periodic of period 2 pi. So it is not injective at all. The inverse function theorem is going to give us local diffeomorphisms, but that are not necessarily diffeomorphisms. So far, we explained the inverse function theorem for differentiable maps between abstract manifolds. Our next stop is the local normal form of immersions. So this is the local normal form theorem for immersions. Consider an immersion between two manifolds M and N. Obviously, right now, these manifolds don't have necessarily the same dimension. What the theorem actually gives us is local charts phi and psi, such that phi is defined in a neighborhood of x in the manifold M, and psi is defined in a neighborhood of f of x for the manifold N, such that the expression of f in these two local charts is this very, very simple map in which the vector x1, x2, xm is sent to the same vector, and then here n minus m zeros. This is, let's say, the local normal form for an immersion from Rm to Rn, okay? And again, our point of view is that this theorem is just a version of the one we already know for differentiable maps in Euclidean spaces. It's nothing else, and let's actually see that that's exactly the situation. Okay? So again, we have here the manifold M, Again, the manifold M, here a point X, here a point f of X, okay? And we consider these local charts, phi and psi, okay? Let's make the picture. Okay, it's a very similar situation to the one that we already considered for the inverse function theorem. At least the picture is similar. And here we consider the expression of f in local charts. What the hypothesis actually says is that the differential of f at the point x is injective, okay? But again, let's remind ourselves that the maps phi and psi are diffeomorphisms. And so, if the differential of f at x is injective, by using the chain rule, we are going to be able of proving immediately that the differential of the local expression at the point phi of x is also injective. In such situation, we can use the local normal form of immersions for the Euclidean case. And the theorem actually says that we can consider here a map alpha, which is a diffeomorphism defined in a neighborhood of phi of x, right? And here a map beta, which is a diffeomorphism defined in a neighborhood of psi of f of x, such that the map that is actually closing the diagram is the one that we considered in the previous slide. So it's the map that sends the vector of the xj's from j equal to 1, from j equal to 1 to j equal to m, to the vector, which is the same one, but considering n minus m zeros at the end, okay? What do we want to prove? What we want to prove is that there are local charts such that the expression of f in local charts is exactly this one. That's our goal, but it is already in the picture because phi is local chart, but alpha is a diffeomorphism. And you have to remember that a local chart is nothing else than a diffeomorphism between an open subset of our manifold and an open subset of an Euclidean space with the usual differentiable structure. So the composition of phi and alpha is going to be a diffeomorphism, and so it's also going to be a local chart, right? That's a very interesting remark. This composition is a local chart in a neighborhood of the point x. Because of a completely analogous argument, the composition of beta and psi is actually a local chart for n defined in a neighborhood of the point f of x. And now you can consider the local expression of f in the local charts phi composed with alpha and psi composed with beta, And this local expression is going to be exactly this one. So indeed, what we are doing is using almost directly the local normal for immersions. It's nothing else. We're not doing anything fancy here. Okay. Something that it is very interesting is that the image of an immersion is not necessarily a manifold. For instance, we can consider these two cases. This is a picture that you can find in the Guillemin and Pollack book. In the first one, we can use the circle to parameterize this figure 8. And what happens is that this, let's say, singular point of the figure 8, the point connecting these two circles, this point has two primitives. And if you want, here we're in a situation in which the figure 8 in the neighborhood of the singular point is going to be the union of two submanifolds. Okay? But it's not going to be a manifold. Because, for instance, this submanifold over here is parameterized by this thing, and this submanifold over here is parameterized here by another open set. So that's a problem. Immersion does not imply injective, and so it is not true that the image of an inversion is going to be a submanifold of the original manifold, or even, and indeed it's not clear that it's going to be a manifold. Here we have another example. This is the line, and what we can do, for instance, is fixing here the point 0, which is going to send to this one, for instance. And when we travel to the right, for instance, we can travel in this direction, and when we travel to the left, we can travel in this direction. The limit when we go to infinity is going to be this point. The limit when we go to minus infinity is going to be also this point. In this way, we obtain a map that it is an immersion, and indeed it's injective. But the image is not a manifold because the image is a figure 8. And the problem here is that we are changing the topology. For instance, if you consider the preimage of a neighborhood of this point, a very small neighborhood of this point, it's going to consist in a very small neighborhood of 0 and neighborhoods of infinity and minus infinity. Okay, so for instance, the preimage of a compact set is not going to be compact because it's not going to be bounded. That's the kind of pathology that we are going to have over here. So the topology is changing. We just saw a few pictures that suggest that the image of an immersion can be very different of a submanifold of the target space. In the next lecture, we are going to see an example that it is especially badly behaved. It's going to be an injective immersion from the line to the torus, in which the image is not a submanifold, but it is a dense subset of the torus. Thank you for your attention.